Hi everyone, in this video I'm going to go through the parts of our review for our Unit 2 test. So let's just hop right in, and the first thing that we want to do is graph this first function, which we know is a quadratic because it's x squared. So key parts of this would be the vertex, if there's any x-intercepts or y-intercepts for that matter, and then finally domain and range. Now, we're just going to go right into the vertex. Since this is in standard form, we have to use the negative b over 2a equation, which gets me an x coordinate of 1/2. If I substitute 1/2 back into the function to get my next y coordinate, I get 1/2 as well. So I'm going to do my best to try to plot this. Okay, that's going to roughly be decent. Now, just by using what we know, my y-intercept has to be at 1. And this graph has to open up, meaning that it's impossible for this to have x-intercepts. My vertex is going to be my minimum. So I'm just going to use some symmetry here to help graph my second point. And so now we have the shape of my parabola like that. So I know that there's none here just by shape. The y-intercept is at y equals 1. Now we could have we could have even found the quadratic formula to find this fact that we would get complex roots, but that's okay that we don't have to in the case that we know. So my domain, negative to positive, my range, well, we know the lowest y coordinate is 1/2 and it opens up, so that would be my range for this function. Now into the second one. Now automatically I don't like this. I don't like that the x quantity squared is second, so I'm going to rewrite it, making sure that my signs stay to the left of the function, or the term that it's in front of, I guess would be the best way to say this. So my vertex here is positive 1/2, positive 5/4. So again, I'm going to do my best to graph this domain. So positive 1/2, positive 5/4, somewhere right around there. Now I want to get my x-intercepts and my y-intercepts. So to get my y-intercepts, it tends to be a little bit easier than my x in this case, but so I'm going to do my y-intercept first. Maybe it's easier to do our y-intercepts in the case that we know it opens, well, we know this is going to open down, so we know it's going to definitely have x-intercepts. So my y-intercept is I'm going to plug 0 in for x into the function. So I end up with negative 1/2 squared plus 5/4, like that. And 1/2 squared is 1/4, but with the negative in front, it's negative 1/4 plus positive 5/4, meaning that we get a coordinate of, or a value of 4/4. So my y-intercept is at 1. All right, and so we can kind of like do a little bit of mirroring there. And next, my x-intercept. So this is where it's a little bit weird. So my x-intercept, I'm going to set the equation equal to 0. This is going to require a little bit more solving work. And we're going to get some square root values. So it's okay that we're going to use a calculator for having to calculate this, or at least estimate it. So I minus the 5/4 on both sides. Since they're both negative, I'm going to change both values to positive. Now I can take the square root. Now, since I'm taking the square root, I got to do plus or minus. So plus or minus square root of 5. Square root of 4 is just 2. So, whoops, we get x equals minus 1/2 of that. And then add the 1/2 to both sides. So I get x equals 1/2 plus or minus the square root of 5 over 2, which as decimals have the approximation negative 0.62 and 1.62. So we're just going to do our best to sketch those onto my graph. So 0.62, negative 0.62, and now we have enough aspects of the function to graph. And lastly, our domain and our range. So my domain, negative to positive infinity, my range, negative infinity to my highest point being 5/4. Okay, And then our last graph, so this one we know is not a quadratic. It is a quartic function, meaning it's x to the fourth. So in this case, we need to see if it is factorable first, just like we do with quadratics, and the last two weren't factorable. But because this is a larger than a quadratic, it's going to require a little bit more work. Now, luckily, it is pretty easy to see that everything has a common factor of x squared. And if I look at this function inside, I can factor it, and I do x minus 1 times x minus 1, so x minus 1 squared. So once I know it's not a quadratic, that's when I need to find the roots and multiplicities. That's how I know when to look for this. So the first root is 0, the second root is 1, and they both have multiplicities of 2. So that means they're not going to cross the x-axis. And so the next thing we need to determine is what the end behavior will be for this graph. If the graph is a positive even function, that means both sides are going to go up. And so the last kind of concept that would be really helpful here is my y-intercept. Well, there's kind of a dead giveaway. Whenever one of your x-intercepts is 0, that also means your y-intercept will be 0. So I don't really need to do any work for this. So if I plot my zeros, one at 0, one at 1, and I sketch in my potential end behaviors, well, now when I go down to connect, I realize I have to make a parabola-like shape because it's a multiplicity of 2. So we basically end up with like a W, like a shape. There's no vertexes for this, so there's no need for us to actually find any more of these values. What we do want to find is the domain and range. Now the domain is pretty easy. It's negative infinity to positive infinity. But now that we've graphed this function, and since this is a kind of unique graph where everything stays above the x-axis, it's pretty easy to say that my range is the y value of 0 to infinity, because even though we don't know the height of a lot of parts, we know that every part of the graph exists on this part. So we do know what the range is. Now in these next two graphs, we're going to deal with the rational function component. And once I finish these graphs here, this is going to be the end of this first video. I'm going to break this into parts just because there's a lot of things that we can do on these graphs. Now when I am solving this graph, I want to see if either the numerator or denominator is factorable. So this one is factorable to x plus 7, x minus 3, or x plus 7. And so interestingly enough, when we cancel, we just get x minus 3 here. Well, that's really it. Because we are not left with a rational function at the end of this graph, all we really want to state is that there's a hole in the graph at x equals -7. I don't know if that's going to show up on our physical graph, but it's something that we want to know. And we're really just going to graph this. Now, we do have a y-intercept of -3. Because, if I'm graphing a line, I just start with the y-intercept. And the slope is 1. So we have an x-intercept of 3. And so my graph would look something like this. And again, if I was to continue all the way down to -7, I think we're going to be off to the side here. So I'd have a hole in the graph somewhere over there. Okay, ooh, that's not what I meant to do. And so my function would just be that. If I want to talk domain, it's -infinity to positive infinity. If I want to talk range, it's -infinity to positive infinity. Oh, actually, I made a mistake here. Sorry. My domain is not negative to positive. It has to skip the hole at -7. And the last part of this graph talks about using arrow notation. So if you remember, that's as x goes to infinity, where's the function going? Well, that's also going to infinity. As x goes to -infinity, where's the function going? Also -infinity. Okay. Now we're going to have a little bit more of a straightforward rational graph. There are no x-intercepts because there's no x term in the numerator, but there is a vertical asymptote at negative 1. Now, even though that technically has a multiplicity of 2, it doesn't actually change how the vertical asymptote functions. Okay, it may mean that our graph does something a little bit more unique. So you don't want to always just assume that the graph does what it, like how it could function without points. Now, there is a horizontal asymptote. If you remember our rules, we look at the denominator's power over the numerator's. Since the denominator is larger, that would be y equals 0. Now I'm doing this in red so you could actually see it. And next thing we want to see, does it have a y-intercept? So we know there's no x because there's nothing for me to solve out of the numerator. So if I plug 0 in, I end up with the value negative 2. And so the general shape of these graphs look like this. Now, normally they are catty-corner on the opposite side of the horizontal and verticals. But as I always keep saying, if we don't have a point to actually support a side, we should get one more point. So if I take the point, let's say negative 2, I end up with the value of also negative 2. So this graph, since it's a squared, actually has both sides going in the same section. So we can do domain. That would be negative infinity to everything except my vertical asymptote. My range goes to negative infinity, but it actually levels out at 0 where the graph never hits. So that would be my range. And lastly, for my end behaviors, as x goes to infinity, the function goes to 0, right? It flattens out. And as x goes to negative infinity, the function also goes to 0. Lastly, it talks about what happens at my asymptote. So when we get closer as x goes to negative 1, both sides of my graph actually venture down. So we would say as x gets closer to negative 1, the function goes to negative infinity. All right, so I hope this video was helpful just for the graphing component. And you can see the next video or two for the remaining part of the review. See you in the next one.